Hello, I am Stephen Wheat. I am a Senior Director for the High Performance Computing Business Group at Quanta Cloud Technologies. Today we will be reviewing the vision and progress towards an adaptive platform for converged high-performance computing and artificial intelligence workloads. The motivation here is that high-performance computing and artificial intelligence have collided. Existing solutions are inadequate for the challenges of sufficiently supporting each community. There is the need for software-defined environment that seamlessly supports traditional compute-oriented HPC workloads and the emerging artificial intelligence workloads. A simple metaphor for this is that of a car and a truck. There are similarities between driving a car and driving a large truck. Each has its needs and capabilities, but the interfaces and controlling mechanisms can be seamlessly similar and familiar to drivers of either type of vehicle. On the one hand, we have high-performance computing that uses substantial computing power with parallel processing techniques for solving complex and advanced problems and performing research activities through computer modeling, simulation, and analysis. On the other hand, we have the various AI domains that use algorithms and techniques that iteratively learn from data to allow computers to find hidden insights without being explicitly programmed where or how to look. In fact, fast-growing data sets and the increase in computing power at affordable costs are driving this convergence of high-performance computing and artificial intelligence. Let's take a closer look at how the technology, tools, and the challenging workloads come together in our solution. Traditionally, high-performance computing, high-performance data analytics, and machine learning have been supported by distinct communities developing different scientific and technical approaches due to the need to target different application domains. Today, the user demand is moving more towards needing a converged solution. A converged platform delivers the computational performance and throughput to train deep learning models, ingest and process real-time data streams, and scale resource-intensive AI workloads. In many converged workflows, AI and high-performance data analytics also allow for creating and refining more powerful high-performance computing models. To make this converged solution real, it needs a robust platform which is able to adapt to different technologies such as CPU, GPU, FPGA, and ASICs. And it needs a consistent architecture with a unified software stack to manage compute, storage, and networking resources. To best design a platform for converged workloads, we need to understand the characteristics of real-world applications in different domains. For example, key EDA applications rely on double precision-based computing power and a parallel file system with high file throughput. In contrast, single precision or even half precision is what is used for deep learning. As depicted in the table, each application domain has its own characteristics with a different mix of compute-bound, memory-bound, or I/O-bound needs. After understanding the workload profile, we should know the strengths and weaknesses of each technology and how they support specific workloads. The CPU has the most flexibility for general-purpose workloads. The ASIC is optimized for specific workloads. The GPU performs well for high-performance computing and deep learning workloads. And the FPGA has a reasonable balance of cost, efficiency, and flexibility. There is no single technology that can fulfill all needs and preferences in a cost-effective manner for all workloads. As with myriad computational workload metrics, storage subsystems have different metrics also, most notably performance, capacity, and persistence. Understanding the data profile and workload demands leads to the best fit storage type and technologies. File systems can be used for hot and cold data storage, and they provide an easier way for user access, but generally have higher costs. Block storage performs the best, but with limited scale, and they usually need NVMe technology to support high performance. Object storage is the cost-effective way for unstructured cold data storage with high scalability. As for the network, There are also different metrics and technologies to support the diverse demands. The very common fat tree topology is widely employed in clusters to support high bandwidth and low latency inter-process communication. A multidimensional torus, on the other hand, is optimized for nearest neighbor inter-process communication. And finally, for extreme large-scale deployments, a dragonfly is a fully connected topology which is suitable for substantially large systems, including exascale. Here we show an adaptive and robust platform with a consistent architecture for converging high-performance computing, deep learning, and AI workloads. Here, all the nodes, including compute nodes, utility nodes, and service nodes, are connected by a dedicated gigabit Ethernet network for out-of-band management. Each node also has extra NICs to connect with specific networks for serving in-band services and accessing data. For example, CPU compute nodes for high-performance computing or GPU training nodes for deep learning rely on the high-performance interconnect fabric such as OmniPath or InfiniBand to boost the performance in computing or accessing shared files. All the compute nodes access the shared data storage pools. Compute nodes utilize a parallel file system to maximally balance the computation and storage needs. The dedicated utility and service nodes have a software stack for serving system management and core services, such as user authentication, resource and job management, system monitoring, and deployment, and more. A key feature of the QCT converged architecture building blocks is the means to simultaneously support several fabrics, even on the most dense compute nodes. Here we transition to the details of QCT's vision and work towards an adaptive converged platform. Today, increasingly more customers are looking for a best practices system which meets specific workload demands. To build an integrated workload-driven system with optimized performance takes much time and many resources. It takes several stages from the initial planning to the final readiness for users. These stages include demand pattern analysis, system design and architecting, system development and deployment, system tuning and performance benchmarking, as well as piloting with friendly users and then going into production. To accelerate time to value for the customer, QCT has designed a pre-validated and pre-configured system concept to shorten the customer's technology adoption and deployment timeframes. This is called QCT POD. QCT POD stands for QCT Platform on Demand. It is a concept of an on-premises, workload-driven design integrated system. Within this concept, QCT will provide various solutions with best practice hardware and software integration for specific workloads. The QCT POD system architecture includes diverse common building blocks, which gives greater flexibility and scalability to meet different customer needs. It also includes management tools to simplify the deployment and management process. And with the pre-validated and pre-configured rack-level system designs, QCT POD solutions also offer suitable power and network cabling to speed up time to market for customers. As for the implementation of QCT POD, it could either be deployed in a converged or a disaggregated structure. In a converged structure, several functional building blocks, such as management, compute, storage, and networking, will be delivered in one rack. While for the disaggregated structure, various building blocks will be separated in different racks for individual scalability and optimal power and cooling management. To best fulfill the workload requirements, it is important to understand the attribute of each building block in the QCT POD. For example, we have big memory, accelerated, and high-density building blocks for the compute. For the storage, we have IOPS optimized, throughput optimized, and capacity optimized building blocks for storage. According to these attributes, we could easily provide the architecture for customers by workload demands. To be more specific, let's look at the general architecture of the QCT POD system. We will deliver QCT POD in management, compute, and storage building blocks, and each of them is connected by the network fabrics. It includes diverse technology components. From the bottom, QCT POD would be delivered using our best-in-class hardware systems. As for the software stacks, it includes open source software recommended by QCT and certain pre-validated commercial software. With various components and building blocks, QCT POD has the flexibility to modify the architecture by workloads. The structure of compute and storage building blocks would be much different between different workloads. Some functions may not even be necessary depending upon the workload demands. However, the management building blocks with dashboard design will always be necessary to provide a simple system management and monitoring capability. In the QCT POD system, no one can directly access the compute and storage building blocks. All control and management will be made in the management building blocks. It is important to make sure all the system resources have been well managed. For the users and developers, QCT POD includes a user interface, development tools, and pre-compiled workload environment to simplify the operation and accelerate the process towards a turnkey solution. With the comprehensive development platform, developers can focus on their specific areas of expertise and gain deeper insights. It is always a big challenge for administrators to deploy and manage a cluster with hybrid infrastructure and diverse services. With QCT POD, administrators can deploy an operating system with configuration management via XCAT and Ansible. The modern web-based dashboards, log, alerting systems, and useful administration tools such as Prometheus, Grafana, Elk, Stack, and Webmin are also pre-built into the system. Additionally, behind the scenes, there are several internal core services such as RMS and Kubernetes, which are supporting the management building blocks. QCT has a comprehensive hardware portfolio to meet the specific demands for each of high-performance computing, artificial intelligence, and deep learning. Pause here to inspect these platform examples. Through our strategic partners, QCT POD includes several storage solution options, all seamlessly integrated. For example, for file storage, we have BGFS, Gluster, and more. For block storage, we also have Accelero. For object storage, we have NetApp and Ceph. Here's an example of how QCT POD simplifies the simulation process with a pre-configured workload package. Prior to QCT POD, each end-user customer would have to compose and integrate the workload environment with a trial-and-error approach to get a satisfactory solution. However, with the workload package already optimized by QCT, the parameters are already tuned. The system is already designed and defined. All the end-user customer needs to do is run their workloads, and the results will be ready with high quality. All of this with substantial savings in time and effort to install and deploy the system. This is a fun slide depicting an AI inference solution running on a QCT POD solution for intelligent video analytics. Perhaps when we meet in person again, we can do a live demonstration. In this talk, we have seen QCT's platform on demand system architecture. First, QCT POD can deliver excellent workload performance with the flexible building blocks design and a pre-configured workload environment based on QCT's outstanding engineering domain know-how. Second, QCT POD system simplifies the management with the admin dashboard, and it speeds up deployment processes with suitable power networking cabling. Third, QCT could accelerate time to value for customers with the pre-validated, pre-configured QCT platform on demand system building blocks. QCT has various end-to-end platform solutions and services based on cutting-edge technologies for different application workloads. We anticipate developing additional QCT POD solutions for many of these vertical use cases. Please feel free to contact us with any questions and interests you may have. Thank you for taking the time to review our adaptive QCT POD platform solution concept. We look forward to seeing you in the marketplace to fulfill your computational and storage needs. This concludes this presentation.
Good afternoon, this is Stephen. I was the one that did that presentation. I'm here to answer any questions that you might have. We can go interactive. I did see a question about FPGA viability and smart NIC viability in the future. I think I got that one coming through okay. So if you have any further clarifying questions about that direction, how I see it personally, I'd be glad to continue along those lines. We can also go a little bit interactive as well. I am a bit curious about the nearly 3 dozen people that were on the presentation here, or observing the presentation. How many have been involved in high-performance computing or deploying artificial intelligence? Just kind of curious as to along those lines. Okay. Bill, I see the first part of the question. Okay, you have. Okay, it's not a question. Okay, fair enough. Thank you. And I'm also curious as to if anyone is in the, perhaps the user side versus the system integrator side of how to service users and customers as to providing for high performance computing needs or artificial intelligence needs. And then for further feedback for QCT, and again, I appreciate everyone participating and paying attention to the presentation. We are quite excited about the solutions coming together for this. Here we go. For large memory requirements. So by large memory pools, I presume you're talking about pools of servers that have, let's say, 1.5 to 4 terabytes of memory apiece. We would be setting up, behind the scenes, we'd be setting up queues that would be aimed at specifically for the workloads for that. And from a solutions perspective, within the workflow, we would set up the job control to send the appropriate jobs to those queues versus to the other nodes. The half-life, as in, Bill, I take it, how do data center providers feel about the half-life of acceleration? So GPUs and FPGAs, in other words, the GPUs and FPGAs are either turning over very quickly or that their lifespan is only so long compared to CPUs. I'm going to presume that it's about the turnover rate that the GPU is moving in technology. I think that I don't. I'll first say I don't know how many of them feel, but I would expect that a lot of them. Okay, turnover rate is that the trend is still moving with adoption, that whatever is fielded is going to have a substantial utility for quite some time through the lifetime of that part, but they would still need to be adding capability to stay ahead of the competition. And so, to some extent, it's quite similar to the days when we saw Intel and AMD innovating at that kind of rate and making decisions about deploying. So it keeps things lively, but it doesn't mean that things have to be traded out, because newer users coming into the fold, first-time users of GPUs and whatnot, the existing technologies a gen ago, 1 or 2 generations ago, are still quite viable for their onboarding. So on the what accelerator cards does it support? I'll have to look into that. In general, we're looking at the active and passive cards for that particular purpose. And we have the RTX series is something that we are trying to expand into support along those lines. Is there a model that you're interested in? Okay, thank you, Vishal. And you'll find that we also support a substantial number of half width and or single width and double width versions of those GPUs as well. But we're relatively conservative in our deployments when it comes to configuring our systems with the GPUs or any other peripheral. We do run it through a validation, and we typically will refrain from validating just every possible combination. But upon significant interest in a particular part, we will explore pushing it through the validation. We don't like sending the system out and then and saying it will work without having actually done every combination of the device to ensure that surprises are not down the road. All right. It looks like we've collected up the questions people are wanting to ask. I do want to thank everyone once again that we are looking at, for attending the presentation. This is a new world indeed, and the level of participation was, didn't know what to expect, and I'm very glad to see you there, and look forward to perhaps hearing from you as you continue your interest in how QCT may be able to be of service to you, either as a technology provider or in helping you to provision to your own customers. And with that, again, I want to thank you for attending, and wish you a safe and healthy day as you go about your business. Thank you very much.